Okay, so this is the module 1 of CET 203 Fluid Mechanics and Hydraulics. Before you go deep into the subject, you first have to understand what is a fluid, what is a fluid mechanics and all. So fluid mechanics is basically the study of behavior of fluids. Okay, mechanics is a study, fluid is another part. Okay, so what is a fluid? Fluid is anything which flows. Okay, that is what you call as a fluid. Okay, it can be gas or liquid. Generally we don't consider solids as fluid because fluids are something which deforms continuously when an external pressure is applied. So neither gases nor liquids can resist, okay, such external pressures. So that's why they comes under the category of fluids, whereas solids, they do have a definite shape, definite volume, and solids have a resistance to the external pressure also. That is the reason when you try to compress a choke, it doesn't get compressed because it is a solid which offers a resistance. Whereas when you have a tank of water and you try to compress it, the water somehow it goes down. Okay, so which means if the those states of matter which offers a resistance to the external pressure, they don't come under the category of fluids, as simple as that. Okay, now moving on to fluid mechanics. As I said, it's a study of behavior of fluids at rest. Now if these fluids, okay, are considered in two aspects, either they are at rest or they are in motion. Now if the fluids are at rest, we call that study as fluid statics. Whereas if they are in motion, again we have two aspects here, that is without considering the pressure forces. Okay, so pressure forces is those forces which causes the motion. Okay, now if they are considered, that is if the pressure forces are considered which causes the motion of fluids, then we call that as fluid dynamics. Whereas if the pressure forces are not considered, then we call that study as fluid kinematics. So three categories of fluid mechanics. Either one aspect is, one study, that is fluid statics, corresponding to those fluids at rest. If they are in motion without considering the pressure forces, it is fluid kinematics. Considering the pressure forces, it is fluid dynamics. Okay, now that completes the basic part. Now we move on to straight fluid properties. Okay, so fluid properties, basically we have four properties in the syllabus, even though there are wide varieties other properties. So we deal with first one, mass density, second, weight density, third, specific gravity, and last it is viscosity. Okay, now we'll straight go ahead with the fluid properties. So the first one is the mass density. Mass density is also called as specific mass. Okay, mass density is also called as specific mass. Okay, now in simple definition, specific mass or mass density is, it is mass by volume. Okay, so as simple as that. We know density is mass by volume. So simply if we call density, it is referred to as mass density itself. So this is mass by volume. Now if you check the unit of mass is kilogram, unit of volume is meter cube. So which means the unit of specific mass is kilogram per meter cube. Okay, so specific mass or mass density, whose unit is kilogram per meter cube. Okay, and it is represented as rho. So we get the equation as rho equal to mass by volume. Okay, now all we need to understand is how rho varies for different fluids. Okay, so first one, or the very basic, is rho of water. Rho of water is always 1000 kilogram per meter cube. Okay, the first and foremost thing you have to learn is rho of water is 1000 kilogram per meter cube. Same way for air, it is 1.2 kilogram per meter cube. So you see the difference also, which means rho of water, that is mass density of water, is much higher than rho of air, mass density of air. Okay, now if you want, you could remember for other things also. For example, gold. We know gold is very expensive. Similar way, the rho of gold is 19,600. And if you consider wood, okay, the rho of wood is 600. Now if you consider mercury, which you just need to have a right view of this, because this might help you in your calculations. And if it is mercury, it is 13,600. Okay, so this is about the mass density, okay, or specific mass. Okay, now moving on to the second one, which is weight density. Okay, mass density was mass by volume. Okay, same way weight density is weight by volume. Okay, so it is weight by volume, and we know weight, the unit of weight is Newton. Okay, so it is Newton per meter cube. Okay, now what is Newton? Newton is basically the unit of force actually. What is force? It is mass into acceleration. So here we consider acceleration due to gravity. So it is mass into g divided by volume. Okay, now earlier we saw that mass by volume was nothing but the specific mass. So specific mass into g it becomes. Okay, so which means the weight density, okay, weight density is represented as gamma equal to rho into g. This is the second equation for that. So when you go to the second parameter, weight density, also referred to as specific weight. Okay, so further now when you hear specific mass, it is the first property, mass density. When you hear specific weight, it is weight density. Okay, so this is another term for that. Okay, weight density. Now we have learned the unit also, it is Newton per meter cube. Now again, how it is varying for various fluids. Okay, rho of water, again we can find out. Rho is generally, rho of water is 1000 kilogram per meter cube from what we learned previously, into g, let's consider it as 10. Okay, now the unit is there, it is kilogram per meter cube, this is meter per second square, so it becomes kilogram per meter cube into meter per second square. Okay, so which means it is kilogram per meter square second square. Okay, so this is how it becomes. Now this is in short written as kilonewton per meter cube. So the rho of water becomes 10 kilonewton per meter cube. Alright, so this is how it goes. So the rho of water is 10 kilogram per meter cube. Similar way you could find out the rho of any other parameters also, or any other fluids also. For example, if you are asked to find the rho of air, okay, again rho of air will be, gamma of air will be rho of air. Rho of air is how much? 1.2 kilogram per meter cube into 10. Okay, now again convert the units into kilonewton per meter cube, or you can express it as Newton per meter cube itself. Okay, so that completes the second parameter. Now moving on to the third parameter. Third parameter is in fact a derivation, or it is derived from the first two parameters. Now specific gravity. Okay, specific gravity is nothing but it's a relative term. It is the ratio of rho of a fluid. Okay, let's say it's a study of, or it's a ratio of rho of any fluid, okay, to the rho of a standard fluid. Like we have something called a standard fluid which we keep as a reference. So if a given fluid has some specific some typical values of specific weight or specific mass, okay, so that weight density of that fluid divided by weight density of a standard fluid, or you could also write it as rho of that fluid, divided by rho of standard fluid. Okay, rho means it's a mass density, so it's a ratio of mass density of that fluid to the mass density of standard fluid. Okay, now in most of the cases all you have to understand is our standard fluid. Okay, whenever we say standard fluid, it is our pure water. Okay, so we consider pure water as the standard fluid. Now we know the standard fluid being water, its values are 1000 if it is rho, and 10 kilonewton per meter cube if it is weight density. Okay, now for a slight example, okay, let's say our fluid is not our standard fluid, the given fluid is water itself. So let's calculate the specific gravity. You can write it as G or S. Okay, now to calculate the specific gravity, okay, we know the standard fluid is water, so considering the mass density of water, okay, now this is a case where the given fluid is also water. Okay, so if the given fluid is water, what is rho of given fluid if being water? It is 1000, so the specific gravity is 1. Okay, similarly if you need to find out any other parameters also, Okay, for example, let's find out for air. Okay, imagine the standard fluid given is air. Okay, if you are asked to find the specific gravity of air, now G of air, okay, will be 1.2 kilogram per meter cube divided by 1000 kilogram per meter cube. Okay, so this is 1.2 into 10 raised to minus 3. Now, what is the unit of this? Since it is a ratio of the same terms on both sides, numerator and denominator, this is unitless. Okay, so there is absolutely no unit for specific gravity. Okay, now moving on to the last parameter, which is called viscosity. Okay, so when you talk about viscosity, you need to understand the definition of viscosity. Viscosity is the resistance to flow of fluid from one layer to another. That is, the fluid actually flows from layer to layer. Okay, now the resistance to the flow of this fluid from one layer, or the motion of this fluids over one layer over the other, such a resistance to the motion, that is what you call as viscosity. Now when you learn about viscosity, you need to understand a law which is called Newton's law of viscosity. Okay, Newton's law of viscosity. Newton's law of viscosity. Newton's law of viscosity states that the shear stress, okay, it says the shear stress is directly proportional to the velocity gradient. Okay, shear stress is directly proportional to velocity gradient. That's what Newton's law of viscosity says. Now let's put it as equation wise. Tau, that is what we represent shear stress as. Tau directly proportional to velocity gradient. So it is dv by dy. Okay. Now in other words, we could also state Newton's law of viscosity as it is that law which states that the shear stress is directly proportional to velocity gradient or angular deformation. Okay, so either velocity gradient or angular deformation or shear strain rate. Not just shear strain, it's a rate of shear strain. Okay, so shear stress is directly proportional to dv by dy. Okay, now let's remove the proportionality by introducing a proportionality constant, tau equal to, okay, so we are here gonna introduce a proportionality constant. So it gives tau equal to mu into dv by dy. Okay, so since we have introduced a proportionality constant which is written as mu, so the equation now becomes tau equal to mu into dv by dy. This particular mu is what you call as coefficient of dynamic viscosity. Okay, so this becomes coefficient of dynamic viscosity. Mu is further now known as coefficient of dynamic viscosity. Okay, now we need to find the unit of tau, unit of mu. So we know tau equal to mu into dv by dy. Now what is the unit of tau, or the shear stress? Stress is basically force by area. So it is Newton by meter square equal to mu into dv. dv means what? It is meter per second. Okay, divided by meter. dy is the change in dimension, change in the length. So it becomes like this. Okay, now Newton per meter square, and let's go derive the unit of mu. Okay, the FM, or the fluid mechanics, is all about units. You need to understand the SI units, CGI units, MKS units and all, and only then you can start deriving the units, and meanwhile through the same strategy you can get at your answers also when you're solving numericals. Okay, so now we need to find mu. The unit of mu will be Newton per meter square. Okay, force per area, which is stress, divided by meter per second per meter. Okay, now solving all this, you get the unit as Newton second per meter square. This is the final unit what you get for mu. Okay, now so which means now we have considered from this equation, okay, we know we have considered all the SI units. Newton is the SI unit of force, meter is the SI unit of length, second irrespective of SI or CGS, it's the same. So all we have got is Newton second per meter square. Okay, now this Newton second per meter square is also referred to as Pascal second. Okay, that is another unit of dynamic viscosity. So the dynamic viscosity unit is Pascal second or Newton second per meter square. This is considering the SI unit. SI unit. Now, if you look at the CGS unit, you can derive the CGS unit now. What is the CGS unit of force? It is dyne. Time, it's the same. Dyne second per. What is the CGS unit of meter? It's centimeter square. So it is dyne second per centimeter square. Now, which we also refer to as poise. Okay, so this is another unit which we come to know, which is poise. Okay, it's a CGS unit of mu or dynamic coefficient of viscosity. Now, 1 poise is always equal to 0.1 Pascal second. Okay, this is another understanding. Okay, so we know that the units of dynamic viscosity or coefficient of viscosity is poise or Pascal second. Okay, now that clears the first part of viscosity. Okay, so now that we know what is viscosity, okay, now we know the units of viscosity. Now we also come across a term called kinematic viscosity. All we learned right now, which is mu. Okay, keeping mu aside, it is kinematic viscosity. Okay, now this kinematic viscosity, okay, represented like, sorry, okay, represented like this. Okay, kinematic viscosity is the ratio of dynamic viscosity and mass density. Okay, so kinematic viscosity is represented as mu divided by rho. Now let's find out the unit. Any parameter you come across, try to derive the units on your own. Mu, what is the unit of mu? It is Newton per meter square into second. Newton second per meter square divided by, what is the unit of rho? It is, okay, unit is kilogram per meter cube. Okay, so that becomes kilogram per meter cube. Now solving this, you get, again Newton we have to convert, because let's make everything in this basic of SI units, the three fundamental units: meter for length, and second for time, and kilogram for mass. Okay, so Newton again you can make it as meter per second square. Okay, meter per second square, this becomes, okay, now cancelling all that, we get the final unit of kinematic viscosity as meter square per second. So that becomes the final SI unit of kinematic viscosity. Now, if we need to derive the CGS unit is definitely centimeter square per second. Here we bring about another term which is called Stokes, named after the famous scientist Navier-Stokes. Okay, so we now have two units. Okay, that is either the CGS unit, which is centimeter square per second, meter square per second. Okay, so we have the CGS unit as meter square per second. Okay, and we have the CGS unit as centimeter square per second, which we also refer to as Stokes. Okay, now what is the relation between Stokes? Like we said, 1 poise equal to 0.1 Pascal second or 0.1 Newton second per meter square. In the same way, 1 Stoke equal to 1 centimeter square per second, which is equal to how many meter square per second? 1 centimeter is how much? 10 raised to minus 2. So centimeter square, it becomes 10 raised to minus 4. So 1 Stoke equal to 10 raised to minus 4 meter square per second. This is the another finding or another unit of expressing viscosity.